This is part 2 of our introduction to the periodic table. In it, we will continue looking at periodic trends, as well as the reasonings behind the formation of chemical bonds and thus chemical reactions. So, let's start it off. The periodic table can be divided up into groups, which are vertical columns, as well as periods, which are horizontal rows. However, for this clip in particular, we'll be concentrating on groups and also the trends associated with these groups. Now, when we're talking about groups and periodic trends, we're really only looking at the representative elements. So that's these guys over here in what I like to call the mountains, just because, well, they kind of look like mountains. All right, these are called the representative elements because they represent the periodic trends very well. All right, you can actually see a pattern going on. These guys in the middle, however, are called the transition elements. And these guys over here are called the inner transition elements. They belong in this little gap over here. And so the reason why we're not particularly interested in these guys, the transition elements, is because they don't represent the periodic trends all that well. It's not as obvious. You can't really see the pattern that clearly. As such, we're going to ignore them for now. Now, just as a reminder, there are two numbering systems. The one in red is the older numbering system. It's not supposed to be used anymore. However, well, it's still popular enough that I kind of had to teach it anyway. All right. So the old numbering system used to be called, well, they called the representative elements the A block. All right. Whereas the transition elements were called the B block. All right. So this used to be called block 1A or group 1A, group 2A, group 3A, 4A, etc., etc., etc. However, with the new numbering system, it's supposed to go group 1, group 2, then this is group 3, group 4, group 5, group 6, group 7, all the way to group 12, and then it jumps over here to group 13. So as you can see in the blue numbers over here. So for our course, I don't really mind which one you use. So if you want to use this group over here, you can call it group 1 or group 1A. This can be called group 2 or 2A. This one can be called group 13 or 3A. So how I remember that is, well, 3, 3, 4, 4. So it makes it a little easier to remember that way. Now, another name for group is family. So for instance, the group 1A elements, they are also known as the alkali metal family. Pretty much every group on the periodic table has a family name, but the most popular ones are, well, alkali metal for group 1A, the alkaline earth metals for group 2A, the halogens in group 7A, and the noble gases in group 8A. So why are they called families? Well, if you're walking down the street and you see two people, how do you know if they are related? Well, obviously if they look the same. So take a look at the members of the alkali family in group 1A. If you have drawn your Boyer-Rutherford diagrams properly, you will notice that they all have one similarity. Now I've drawn my Boyer-Rutherfords very simply, so I haven't actually drawn the core electrons, just the outermost of the electrons, the valence shell electrons. If you look at the group 1A, you'll notice that they all have one valence electron. So, over here, one valence electron, one valence electron, one valence electron. So even though they're inner cores, they have multiple shells or different number of shells, it's the outer part that looks pretty much identical. And because it looks identical, they are going to behave almost, well, very closely to each other. They will have similar physical and chemical properties. So, for instance, the alkali metals react very violently with water to produce hydrogen gas. And because this is an exothermic reaction, interesting. And as it is an exothermic reaction, the hydrogen does ignite to cause a, well, explosion. So, to summarize, alkali metals, one valence electron for every one of them, and they all react violently with water to produce hydrogen gas. So that's why they are called a family, because they all have similar properties due to their one valence electron. The halogens, on the other hand, in group 7A, or 17, they all have 7 valence electrons. All right? And this makes them extremely reactive as well, especially with organic materials. So, for instance, fluorine, chlorine, iodine, and bromine. These are usually used as disinfectants in pools. When we use chlorine and bromine to kill off bacteria, we'll use iodine to clean wounds. This is all because the 7 valence electrons allows it to be very reactive, and it kills off a wide variety of organic tissue. So, to summarize, halogens have 7 valence electrons. They are extremely reactive, especially with organic substances, and they're used as disinfectants. And now we have the last family, the noble gases, which are located in group 8A or group 18. These guys all have a full valence shell. So if you take a look at helium, helium can only have 2 valence electrons, or 2 electrons in the first shell, and so it has 2 right there, nice and filled. Neon can have 8, and so can argon, and they are all filled with a full, complete outer valence shell. So the interesting thing about this family is that they are extremely stable, extremely unreactive, these chemicals, or these elements rather. So, to summarize, noble gases, group 8A or 18, full valence shell, extremely stable and unreactive. So, now that we have some background information about the periodic table and its elements, let's talk about chemical reactions. In general, a chemical reaction will occur only if the newly formed product is more stable than the original reactant. So what I mean is, the substance that it was before will only go through a reaction if the new substance is more stable. I mean, that just makes sense. If what it was before goes through a reaction and becomes less stable, it's not going to exist very long. And so why would the chemical reaction go forward? So if it doesn't exist, well, you don't have to worry about it. Now, of course, this is in general. There are always exceptions to the rule, but usually this is the case. So the question now becomes, how do you achieve this stability? That's where we look to the most stable elements on the periodic table, the noble gases. Now everyone in this family, group 8A, the noble gases, is extremely stable and unreactive, and that is due to its full valence shell. So, since a full valence shell provides stability, atoms will lose or gain electrons to become stable. Alright, so let's take a look at an example. One other thing, this statement over here is essentially known as the octet rule. Right? And the octet rule essentially states that when an atom has 8 electrons, or rather a full valence shell, it is going to be stable. Alright, so back to our example. Sodium. Sodium has 1 valence electron, and like I said above over here in the octet rule, in order to be stable, sodium needs to have a full valence shell. So, there are 2 options at this point for sodium to become stable. The first is, well, gain 7 electrons. Right? If you gain 7 more electrons, 1, 2, 3, 4, and I'm running out of space for some reason, 5, 6, 7, 8, or there we go. So 1, 2, 3, 4, 5, 6, 7. By gaining 7 electrons, you get a full valence shell. So that will do it. The second option, though, is to lose 1 electron. So if it loses this 1 electron, then this whole shell disappears. You know what? I think I can make it disappear. There we go. Disappear. And once that shell disappears, lo and behold, we've got a full valence shell. So, lose 1 electron. Now, if you're a sodium, which one would you rather do? Which one's easier to do? Obviously, losing 1 electron is much easier than gaining 7 electrons to achieve stability. Let's take a look at chlorine now. Chlorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And again, also has 2 options. First option, gain 1 electron. Alright, so if I tack on one more electron, there it is. 1, 2, 3, 4, 5, 6, 7, 8. Full valence shell, stability. The alternative, of course, is to lose 7 electrons. And so by getting rid of the 7 electrons over here, 1, 2, 3, 4, 5, 6, 7. Well, there we go. We lose the whole outer shell, and now it is also stable. Of course, which one's easier to do, though? Gaining 1 electron or losing 7? Obviously, gaining 1 electron is a much easier option. Now, I want you to take a look at your Bohr-Rutherford diagram assignment, or your little worksheet, if you had already finished it. Take a look at sodium, how its Bohr-Rutherford is drawn. Notice how it looks a lot like the noble gas neon. I mean, take a look at them. 2 shells, 2 shells. 8 valence electrons in the outer shell, 8 valence electrons on the outer shell. So essentially, by achieving stability, the atom resembles the noble gas that it is closest to. This is called isoelectronic. Alright? So sodium is said to be isoelectronic with neon now, because they have the same electron configuration. And electron configuration basically means the way the electrons are set up, or the pattern, the shape that they have right there. And of course, if you take a look at chlorine, it is going to be isoelectronic with argon. Right? Because they have the same electron configuration as each other. Okay. So let's go back to sodium. By losing that 1 electron to achieve stability, sodium is now considered to be an ion, which is essentially a charged atom. Ugh, I can't even write. Charged atom. Now the reason why it's charged is because it's lost an electron, and electrons are negative, right? So because it's lost an electron and it was negative, it is now more positive, positive by 1. Take a look at it. Sodium has 11 protons, so 11 positive charges, and it should have had 11 electrons. But because we threw one away or took one out, it now only has 10 electrons. And remember, electrons are negative and protons are positive. So now overall 10, 10 over here, they subtract, and we're left with that 1 extra proton, and that's where we get the 1 positive charge. To show this, you need to put square brackets around it, and you need to write the charge in. Now you don't need the little circle over here, so I'm going to erase that. But this is a properly drawn sodium ion. Alright? Square brackets to show that this was not the original atom and that it has changed. The electron has moved out. And we show the charge to show what is the charge now. 1 positive. Let's take a look at chlorine. By adding an electron to chlorine, you have also turned it into an ion, a charged atom. Right? To show, once again, to show that it's a charged atom, put square brackets around it, and you must show its charge. Now, chlorine has 17 protons. 17 protons. Right? And it technically should have 17 electrons as well. But because you added an extra electron, it now has 18 electrons. 18 negatives for every 17 positives, meaning that the charge at the end is 1 minus. So this would be a chlorine ion. Now, ion is a very generic term. To be a little more specific, if you have a negative ion, it's called an anion. Alright? If you have a positive ion, like we have here with sodium, it is called a cation. Alright? So cation are positive ions. Anions are negative ions. How do I remember this? Well, essentially, if you take a look at the cat, the T kind of makes a positive sign.